So we were looking at triple integrals and using them to compute volume and then possibly mass. Okay, so the last thing we were talking about, we talked about looking at a triple integral on a rectangular block. And we did a Riemann sum, a very brief discussion. Then we evaluated a triple integral on a parallelepiped. We computed that integral and we went on to applications, finding the centroid of three-dimensional regions, talked about moments of inertia that you can actually compute. And then we started looking at whether or not a integral is z simple, y simple, or x simple. So I want to do a couple of examples. Okay, so we want to find the volume of the region T that is above the XY plane and bounded by the elliptic paraboloid Z equaling x squared plus 4y squared and the cylinder x squared plus 4y squared is equal to 4. So how would I actually set this up? Well, the first thing I need to know is that the base.
Scroll up real quick, please.
Yes, Silas?
Yep.
How can I help you?
Can you scroll up real quick, please?
Oh, yes. Hang on one second. I certainly can. To here?
Yep, right there.
Okay.
All right, I got it. Thank you.
So the base or the bottom is Z is equal to 0. And the top is Z is equal to x squared plus 4y squared. So the question is, so we already know what's floating over top and we already know what's at the bottom. So from here, we can get that 0 is going to be less than or equal to Z, which is less than or equal to x squared plus 4y squared. So now what is difficult is we need to find the region in the XY plane. So we already know that our volume is going to be the double integral over our region. We know Z goes from 0 to x squared plus 4y squared. And then we have dz. So that part is there, but what we need to figure out now is the dA. And so now we need to look over in the XY plane. And so if we project our cylinder to the XY plane, this thing looks like what? What will we get in the XY plane?
A parabola.
Circle? Oh no.
Wow, I got a couple different answers. Okay, well, let's see. So we have x squared plus 4y squared is equal to 4. No mention of z. So in the xy plane, that's what we're going to get. So we're going to get x squared over 4 plus y squared
Ellipse.
and equal to 1. Good. So we're going to get an ellipse. So our ellipse, well, x goes over to 2, and y goes up 1. So our ellipse looks like this. And you know, there really is no easy way to find the integral over an ellipse. There really isn't. We have to assume that the top half of the ellipse is, this top half is y is equal to the square root of 1 minus x squared over 4. And the bottom half is y is equal to negative square root of 1 minus x squared over 4. So there really is no very nice way to do that. So I can see that if I fix x, y is going to go from one curve to the next. And then the x is going to sweep out from -2 to 2. So our volume, whoa. So our volume is the integral x goes from -2 to 2. Y is going to go from minus the square root of 1 minus x squared over 4 to the positive square root of 1 minus x squared over 4. And then z is going to go from x squared plus 4y squared to x squared. Oh, I'm sorry. Starts off at 0 to x squared plus 4y squared. And now I can do dz, dy, dx. And that becomes the volume. Not very easy to integrate. So a problem like that I would give you would be a setup, but do not integrate. Okay, so that one would say set up, but do not integrate. Okay. Next example is to use triple integration to find the volume of the tetrahedron T. And so I have to draw T. Okay. Okay, so this is the tetrahedron T. This is the point 1, 0, 0. This is the point 0, 1, 0. And this is the point 0, 0, 1. Okay, so you can find out from just a little bit of work that this turns out to be the line y is equal to 1 minus x. Okay, so if you just project that down to the xy plane, you can find that. And then you can also find that this surface is z is equal to 1 minus x minus y. So over in the xy plane, so over in the xy plane, this is z, y is 1 minus x. So we can now say that z goes between 0 and 1 minus x minus y. And then we can say that if we fix an x, it goes from there to there. So we can say that y goes from 0 to 1 minus x, and then x, well, this line starts all the way over here at 0 and it moves all the way to 1. So we can say x goes between 0 and 1. So therefore the volume of this tetrahedron is the integral from 0 to 1, the integral from 0 to 1 minus x, the integral from 0 to 1 minus x minus y, dz, dy, dx. Okay, and we did this integral before. It just comes out to be 1/6. Okay, now suppose the question asks, now find the total mass of the tetrahedron if its density at each point XYZ is rho of X, Y, and Z is equal to XY. Okay, so now we're just going to take our mass is the triple integral over the region T of our density dV. So what's cool is we've already figured out this part and this part. That's already been done for us because we figured it out when we did our volume. So this now just becomes the integral from 0, 1, the integral from 0 to 1 minus x, the integral from 0 to 1 minus x minus y, and now I need the density function, which is xy, and now I have dz, dy, and dx. So I can actually pull, whoa, I'm trying to figure out what I did wrong that it won't let me. There we go. Okay. So because there's no z here, I can actually, if I want, I can pull this xy out to here. I can even pull the x through, but what I can't do is pull the y. I can pull that out just so I can integrate with respect to z, but it really doesn't matter. This answer turns out to be 1 over 120. Okay. All righty. Now I want you to find the centroid of the tetrahedron. All still the same problem. Still the same problem. I haven't started another example. So the x-coordinate of the centroid is 1 over the mass, the triple integral over the region of x times the density dV. So the mass we said was 1 over 120, so therefore the x-coordinate becomes 120 times the integral from 0 to 1, the integral from 0 to 1 minus x, the integral from 0 to 1 minus x minus y. So I'm going to take x and multiply by the density, which was xy. So that's going to give me x squared y dz dy dx. The y coordinate is going to be 120, integral from 0 to 1, integral from 0 to 1 minus x, integral from 0 to 1 minus x minus y. I'm going to take xy and I'm going to multiply by y. So that's going to give me xy squared dz dy dx. And lastly, the z coordinate is going to be 120. The integral from 0 to 1, the integral from 0 to 1 minus x, the integral from 0 to 1 minus x minus y. And now I'm going to have xy, but I'm going to multiply by z, dz, dy, dx. Okay, so there are several things that we can do with these triple integrals. Okay. So now let's move on to a completely different example. So this one asks us to find the mass of the solid above the XY plane bounded by the cone.
The cone.
Oh yes, the cone. We haven't
Hey,
seen a
Dr. Locke.
cone in a while. Use a cone. Wait a minute. I ain't seen a cone. What you talking about? The cone, 9x squared plus z squared is equal to y squared, and the plane y is equal to 9 if the measure, oh, wait till you're integrating underneath hyperbolic paraboloids and things like that, and the measure of the volume density at each point x, y, z in the solid is proportional to the measure of the distance from the point to the XY plane. Now that sounds rather difficult. Okay, I like this problem because it's wordy and it makes you think. Oh, goodness gracious, it's wonderful. Okay, so we have a cone. All right, now we haven't had a cone in quite some time. So this cone looks like not, so the cone is defined by 9x squared plus z squared is equal to y squared. All right, so now we've looked at cones before. So in the past, we looked at cones that look like z squared maybe equal x squared plus y squared. And so when we had something like z squared equal x squared plus y squared, we always went to the xy plane. Whoops, that's the wrong thing. We went to the xy plane And when we went to the XY plane, we said, well, Z is 0. So it was just a point. And then when we looked at any other value of Z, we were able to get that if we looked in the ZX plane, so this is the ZX plane, we just got something that looked like, I don't want that. So in the ZX plane, we got something that looked like this. Now you know that's not supposed, that's supposed to be a straight line. Thing's supposed to be crooked. So in the ZX plane, we got something that looked like that. In the ZY plane, we got something that looked like this. And so from there, we were able to say, oh, wow, I can actually see come on now, do right, do right, do right. Thank you. I can actually see, okay, that was supposed to be green, but it didn't work. I can actually see the cone. So you guys should, so that was this problem. Well, guess what? This is also the ZY plane. I did them both over here. This one now is Y is equal to 9x squared plus Z squared. So this one looks like, this one has a completely different look. It's shaped, it opens up in Y. So this cone So this cone opens this way. Okay. Oops. So we're only concerned about then the part of the cone that is over top of the XY plane. So this is what our region looks like. That's not right. Okay, there you go. because it's cut off by right here, y is equal to 9. So this is the region that they're talking about, okay? The other part that, so you can actually see here that we can then define this top to be z is the square root of y squared minus 9x squared. So that's what that's going to be. And then it said that the density is defined by the distance to the xy plane, and that is just z. So the density, rho, of xyz is proportional to that, so it's equal to some constant times z. Okay, so now we have that our mass, what are we trying to find? The mass? Yeah. So that our mass is equal to the double integral over the region. I know z goes from 0 to the square root of y squared minus 9x squared. And then my density is kz. And then I have times dz, dy, or dA. So now what we need to figure out is what is what does this thing look like? So in the XY plane, this cone comes down on the XY plane. So Z is 0. So in the XY plane, Z is equal to 0. So what is the cone? The cone in the XY plane is hitting it as such. Okay. So you have y is equal to 9x squared. So those are lines.
That's plus and minus 3x, right?
Say that again.
That's plus and minus 3x, right?
Plus, yes.
Oh, okay.
So this is, so I was going to say, this is y is equal to 3x, and y is equal to y is equal to minus 3x. Okay, so here's where it gets a little scary, guys. This is the y-axis. So the region that this thing is over top of is here. Remember, it's facing the y-axis. So the cone is over top of this part up until y is equal to 9. Okay, so the best way to do this is to fix a y and let x go from this curve to that curve. So now we're going to get the mass x is going to go from minus y over 3 to positive y over 3. Okay, y is going to go from 0 to 9. And then this goes from 0 to square root of y squared minus 9x squared. And then I get kz dz dx dy. So the big mistake that would have been made here would have been if we thought that the region was over here, and it's not. We have to remember that this thing is facing the y-axis. So the way it's coming down on the plane, whoa, baby, go back. The way it's actually coming down on the plane in the XY plane is like that. Okay, this answer, please work it through, turns out to be 729 over 2K. Any questions? Any questions?